Okay, so the first question asks for the identity of element X. Well, we know it had a red flame, and red flame either comes from lithium or strontium. Okay. And then it says that when it's placed near a magnetic field, there's no movement. So if we do the configuration for Li, using the orbital notation, we have He2S1. Okay, so that equals Li. And then if we do it for Sr, we have Kr. And then we have 5S2. Okay? And that equals Sr. So we see that this one here has one unpaired electron. So this is going to be drawn towards a magnetic field. So we know that it can't be that. It's going to be Sr. Remember, if all the electrons are paired, there's no magnetic field. So we could say Sr, we could say all electrons are paired, thus no movement towards a magnetic field. Okay, and we see that based on that right there. So now let's balance and classify this reaction. So we know that this is now Sr. We know that this is Sr. So let's balance it first. We see 2 Cls there and we see 3 there. So I'm going to do 2 and I'm going to do 3. That makes Als 2. Okay, and that makes SRs 3. So for balancing, we can see above. For classifying the reaction, we have a single element replacing another single element. So this is single replacement. You'll learn later on that this is also a type of oxidation reduction reaction. So when 10 grams of X and 40 grams of AlC are present, what mass of XlCl2 is produced? And what mass of excess remains? Okay, so this is going to be your typical ice chart. So we know that we have 3 Sr plus 2 Al goes to 3 SrCl2 plus, this is 2AlCl3, plus 2 Al. So we're going to make a line through that. There. Make a line there. Okay. And we have ICE. So you have 10 grams of X. So remember, we have to always convert that to moles. So the molar mass of strontium is 87.6. So you have 87.6 grams in every 1 mole. This is for strontium. Equals 10 grams per every X moles. So X is going to be equal to 10 divided by, let's go 10 divided by 87.6, 87.6. So that's going to be 0.118. You can take these out however much you like. We're going to round for significant figures at the end. So this is 0.118 moles. And 40 grams of AlCl3. Let's go ahead and do that here. So the molar mass of AlCl3, here's what I like to do, since I'm lazy. Molar mass of AlCl3. And it says the molar mass is 133.34. So I have 133.34 grams in every 1 mole. Remember, the molar mass is always on this side. It's equal to 40 grams per every X moles. So, away. So X equals 40 divided by 133.34. That equals 0.300. So this is 0.300 moles. And this is 0 moles. and this is 0 moles because the reaction hasn't happened yet. And this is going to go down by 3x only when you compare it to this, who's going down by 2x. And this is going up by 3x, and this is going up by 2x. So these all relate to one another here. So there needs to be a 1.5 times more SR than AlCl3, and we don't have that. So we're going to run out of that right now. And let's go ahead and solve for x down here below. So 0.118 minus 3x equals 0. So 0.118 equals 3x. So x equals 0.118 divided by 3. 0.118 divided by 3 equals 0.039. So x equals 0.039 moles. Okay. So if we put 0.039 back into there, you should get point. So if you took that like times 3, you get like 0.118. Okay. But what we're going to do is we're going to put it right into here. Okay. So this is going to become minus 2 times 0.039. Now, what a lot of people forget is what we have to do is take 0.3 minus that. So what we're doing is 0.300 minus 2 times 0.039. And that's going to give us what we have at the end there. So 2 times 0.039 equals that, 0.078. So 0.3 minus 0.078 equals 0.22. 2 moles. Okay. And then what we have to do is now take 3 times that. So this is 3 times 0.039. So 3 times 0.039 equals 0.117. And 2 times 0.039. So 2 times 0.039 equals 0.078. So technically the problem is done at this point, although the first one asks for mass of X Cl2 produced. So why don't we do the answers down here. So XCl2, we know that that's SrCl2, and we made this many moles. So we got to convert that to grams. So let's do that first. So what we're going to do is look for the molar mass of SrCl2 first, because I'm lazy. Molar mass of SrCl2. The molar mass of SrCl2 is 158.53. So this is going to be for SrCl2. So we have 158.53 grams in every 1 mole. X grams in every 0.117 moles. So we're going to take 0.117 times 158.53. And that's 18.548. And if we look up here in the problem, we have 2 significant figures because there are 2 here and 2 here. So we're just going to call this answer 19. 19 grams of SrCl2. That's the first answer. And then it said mass of excess remaining. Okay, so this is the answer to 1. 2 is going to be this. The grams. So we already did the molar mass of that right there. So we have it grams in every 1 mole is equal to X grams in every 0.22 moles. So that is equal to 0.222 times 133.34. And that's equal to 29.6, but we're just going to round that up to 30 grams of that excess. Let's move on to the next problem. So we have photoelectron spectra for these, we see that this is the high side and the low side simply because the numbers are high. So let's go ahead and just decode these real quick. This is going to be 1s2. You always start with 1s2 because it's closest to the nucleus. This is 2s2. That would be 2p2, 2p4, 2p5. This is 2s2, 2p5. So element here is fluorine. This is one peak, so it's either helium or hydrogen. But we see later that it's going to be going into a compound, and we know that noble gases cannot bond at all. So this is now going to be hydrogen. And element C here, again, high, low. Don't get thrown off by the size of these peaks. They're relative to one another. So the first one's always 1s2. That makes this 2s2, and that makes this 2p2. So we know that element C, ironically, is C. Okay. So provide the Lewis structure. We'll answer these down here. Molecular geometry and polarity for A, B. So that's HF. So if you do want minus have divided by 2, you're going to get this. The molecular geometry for that is linear. So that's the only option. And the fluorine is more on the right. So this is a polar molecule. Okay? Include partial charges. So fluorine is pulling harder on those electrons. You can think of the arrow pointing towards fluorine. And that's a plus right there. Okay? Provide the Lewis structure, molecular geometry, and polarity for CB4. Okay, well, we know that B is H, and that's C. So CH4, that's methane. Want minus have divided by 2 should give you a structure like this. And we know that that actually is a 3D molecule that is forming that shape, and we know that that is called a tetrahedral. Immediately, if all you see is carbon and hydrogens, you know that it's going to be non-polar. And if it's non-polar, we see no partial charges. No partial charges. If they are there, they cancel out, kind of like in CO2. Okay? Now let's do C. So when 0.4 grams, the more ideal gas. So we know that this is going to be the more ideal gases because ideal gases should expand, and things that expand should only have London dispersion interactions. And to only have London dispersion, you need to be only nonpolar. In this case also, that very nonpolar CH bond really is something that we should draw our attention towards. Okay, so you see here that they give us a volume. They're asking for pressure. This ultimately can be turned into moles, and there's temperature. So they want the pressure, so we're going to use PV equals nRT. P equals nRT divided by V. Okay, so we're going to have to convert those 40 grams of CH4. So CH4 is 16 grams in every 1 mole. You have 40 grams. I think it was 40 grams, right? Yep, no, 0.4 grams. X moles. So 0.4 divided by 16 equals 0.025. So this is 0.0. So X is equal to, so 0.025. We know that R is 0.0821. We know that the temperature is going to be this plus 273. So 35 plus 273 equals 308. I could have done that in my head. 308. And the volume is going to be this 123.250 liters. So if you take 0.025, you multiply that by 0.0821, and that equals that. You multiply that by 308, that equals that. You divide that by 0.250, that equals that. So the pressure should be, hi guys, and you have two significant figures, so the pressure should be 2.5 atmospheres. To be continued. Holler. All right, so that completes that problem. Let's go on to this next problem. Again, we're seeing a theme of photoelectron spectroscopy decoding things. So element Y, there's the high side, there's the low side. Watch out, I might put the high side over there. 1s2, 2s2. Anytime you go over here, that's got to be 2p6, 3s2, 3p1. So now that's our old friend aluminum. Element Z, again, it's just one, and we're probably going to make a bond. There it is. So we know that that's got to be our old friend 1s1. So that's got to be hydrogen. No. This is 3p3. That's ridiculous. So that's P. 3s1. 3s1 would be right there, Ramsey, you silly guy. Okay, so let's do A. Provide the Lewis structure, molecular geometry, including all partial charges, for YZ3. So PH3. So when you do PH3, that's going to look like this. When you do want minus have, the molecular geometry for this is going to be trigonal pyramidal. Remember, the shape for this has 2 in the plane of the board and 1 going out, or we could do it going back if we like. This is a 105-degree bond angle, by the way, and this up here is a 180-degree bond angle, and this right here is a 109.5-degree bond angle. Got to know your bond angles. Okay. Now, partial charges. Well, P pulls harder on those electrons, and they don't cancel out. So there it is. And this is polar. Okay, so let's do B. Do you predict it to mix better with H2O or CO2? Well, if we do the Lewis structure for H2O, we see that we have a polar molecule with charges. And if we do the Lewis structure for CO2, we see that those charges, okay, they're there, but they end up canceling. Okay, so if mixing is just charge attraction, it's going to mix better with water. Okay, they're both dipole-dipole. And let's draw that interaction and how it's going to look. Okay, and then we could have the P right here with this partial negative lining up right there. And since they're both partial, this is called a dipole to dipole interaction. And this is a good enough explanation for that. Okay. Oh, and then we're going to have CO2 in the mix as well. So let's say this is the container. And CO2 is going to be over here by itself. That's really ghetto to have it out like that. Okay, flying right past it. Now it does notice it a little bit. Those partial charges can exist. In AP chemistry, you're going to learn that's called polarizability, or the ability for a temporary dipole to exist in something that's nonpolar. Either way, there's a long distance away, so we call that a London dispersion force. So again, photoelectron spectra for 2 more. Element G, here's that 1s2, 2s2, 2p6, 3s2, 3p1. There's that aluminum that I was looking for. And, oh, they swapped it. Here's that high side. Don't trip. 1s2, 2s2, 2p3. So that is nitrogen, I believe. Yes, it is nitrogen. So element G reacts with element H2 to produce compound G. So element G, which is Al, reacts with H. Oh my gosh. N2 to produce element GH. So it's Al2N3. Oh, what am I talking about? They're both, one's +3 and one's -3. So it's ALN. What the heck am I talking about? So this is 2, so I'm going to do 2 here and 2 there. So write and balance and classify this reaction. This is a synthesis reaction. Okay, so now we're going to do an ice table for this. I really don't have enough room here. So 0.5 grams and 0.5 liters of that are going to react. So what we're going to do is I'm going to go find another area to do that table. I'm going to say C somewhere else. I'm going to say here. So this is going to be, this is where I'm going to do 4B. So this is going to be C last page. So there is 4B. And in 4B I have AL plus N2 goes to AL N2 to ICE. Now everything that goes in here has to be moles. So we have 0.5 grams of Al and 0.5 liters of H2. So let's do Al first. Al, you have 27 grams in every 1 mole. You have 0.50 grams X moles. So 0.5 divided by 27. So clear. Second one. So 0.5 divided by 27 equals, is that what I have? Yeah. Equals 0.0185. 0.0185 moles. So that's going to here, 0.0185 moles minus 2x. So here you have 0.5 liters, and since it's an ideal gas, if PV equals, so this is for H2, and RT, N equals PV over RT. So what is your P? Your P in this case is 1 atmosphere and 25 degrees Celsius. Okay, so P1, this is 0.5, this is 0.0821, this is 298. So 0.5 divided by 0.0821 equals that, divided by 298 equals that. So 0.020. 0.020 moles. So this is 0.020 moles. And then this is 0 moles. So this is minus x, and this is plus 2x. So in this case, you need 2 times as much of that, but you don't have it. So that's 0. So 0.0185 minus 2x equals 0. So x equals 0.0185 divided by 2, 0.09925. So if I put that in here, 0.00925. So 0.02 minus 0.00925. That equals 0.01075 moles. And if I take 0.00 925 times 2, that equals 0.0185 moles. And then what is 4b even asking for? What mass in grams of GH is produced? So they want a mass of excess reactant. So mass here in grams and mass here of excess reactant. So now we're at this point where we have to convert each of these to grams. So let's go ahead and put our answers here. They wanted the mass of GH is produced and the mass of excess reactant that remains. Okay, so mass of GH that's produced, well, we have 0.0185 moles. So what is the molar mass of aluminum nitride? Molar mass of ALN. Molar mass of ALN is 41. Why don't we just say 41? Notice it wasn't 2 ALN. The 2 was taken care of here. So I don't do 2 ALN. So 41 grams per every 1 mole is equal to X grams per every 0.0185 moles. Okay, so now I'm simply going to cross multiply, and I'm going to go I forgot that 0. Shoot. 0.0185 times 41. That equals 0.7585. So 0.7. But how many sig figs are there? Dang, I was forgetting that. Okay. There are 2. So 0.76 grams of ALN are produced. And we have N2, so we know that that's going to be 28 grams per mole. So we have 28. There's a community meeting. Yeah, we don't have intercession today. Or 28 grams per every 1 mole equals X grams per every 0.01075. Sorry, Kev, I told you. I thought we were going to have the study hall, but there's a community meeting. 0.01. Yeah, sorry. So 0.01075 times 28 equals 0.30 grams of N2. All right, so that's the answer of how much excess N2 remains. And now let's go ahead and do this last question. So this one here is going to be a tad bit nar, but I'm going to try my best to do the ice table over here for this one. Okay, so we have NaN3 plus Fe2O3 goes to Na. Actually, I'm not going to do it there. Where am I going to do it? Let's just look at it first. So what mass of excess reactant remains? What volume of nitrogen gas is produced? And what mass of excess remains? All right, so let's go ahead and do this problem. I'm going to do it here. Okay, so this is going to be A. So we have NaN3 plus Fe2O3 all right, so it's azide plus Fe2O3 goes to Na2O plus Fe. What's that 2? So we got to balance this first. So I'm going to put a 3 there. I'm going to put a 2 there. Um, put a 3 there. Gonna make that a 6. And then that's gonna end up with a 9 here, a 2 here. I believe that's balanced. Let's check. 6 NAs, 6 NAs. 18 ends, 18 ends. 2 FEs, 2 FEs. 3 O's, 3 O's. So we should be good. Okay. So let's go ahead and just set up this ice table because I know that's going to happen. Anytime you have a reaction with numbers, we're going to do some cooking. Okay. So this is 0, 0, 0 plus 3x plus 2x plus 9x. This is going to be something minus x, and this is going to be something minus 6x. And, okay, it contains 17 grams of NaN3 and 250 grams of Fe2O3. So we have 17 grams of NaN3. So let's do the NaN3 first. We got to convert that to moles. So sodium azide, we're going to do our typical molar mass of NaN3. I know you guys could do that. That's going to be 65. All right. So you have 65 grams in every 1 mole equals 17 grams for every x. So 17 divided by 65 equals 0.262 moles. So this is going to be 0.262 moles. And molar mass of Fe2O3, iron 3 oxide, if I remember correctly, that should be around 159.7. Okay. So for the, sorry, it's so ugly. Fe2O3, so 159.7 grams in every 1 mole, 250 for every x moles, because they gave us 250 grams initially. So I'm going to take 250 divided by 1, 250 divided by 159.7, 1.57. Okay, so you need 6 times as much NaN3, and you definitely don't have that. You have way more of this, so that's an excess. We're using up all that azide. It makes sense because nitrogen is going to end up being the really important thing here. So that's going to be to 0. So when you solve that, if you take 0.62 moles minus 6x equals 0, and then you take 0.262 divided by 6, we're going to get x as 0.044. So x is 0.044 moles. So if we take 1.57 minus 0.044, we get 1.526. So we use very little of this. That makes sense. 1.526 moles. And if we take 3 times 0.044, we get 0.132 moles. And if we take 2 times 0.044, we end up with 0.088 moles. And if we take 9 times 0.044, we get 0.396 moles. Okay, so let's look at what they want from us. What volume in liters of nitrogen gas? Okay, so that makes sense. It's an ideal gas. That's what's protecting us. So we want that in liters. And then they want mass of excess reactant that remains. Okay, so then they want this, and we're going to convert that to grams. All right, so I don't even know where this. Let's just go up here, I guess. Okay, so V equals nRT over P. V 0.396, 0.396, 0821, and T in this case is 21 degrees Celsius, so 273, 293, 294 Kelvin divided by P, which is 0.90 ATM. So let's put that in our calculator. So 0.396 times 0.0821 equals that, times 294 equals that, divided by 0.9 equals that. 10.6, that makes sense. But let's see how many sig figs we got in this parabola. Something tells me there's 3, 2, 2. So I'm going to go with 11. So this is going to be 11 liters. 11 liters of N2. Mass remaining, okay, so we have that Fe2O3. We know that the molar mass of Fe2O3 is 159.7. So this is N2. The Fe2O3, 159.7 grams in every 1 mole equals 1.526 moles, so X grams and 1.526 moles. So 1.526 times 159.7 equals 243. So 2.4 times 10 to the second grams of Fe2O3. All right. Do you predict the initial pressure inside the airbag to be higher or lower if the temperature is increased? Okay, so it's going to be higher. Okay, justify your answer by drawing a graph. Okay, so we know that temperature and pressure are directly related to one another, assuming the volume has already reached maximum capacity. So if we have PV equals nRT and the volumes reach maximum capacity, that's constant. We know that the moles in this case are constant because it's a sealed container. So that means the pressure is basically proportional to temperature in that case. C, clearly explain why nitrogen gas is appropriate for an airbags. So the Lewis structure for nitrogen is that. So it's a small molecule. Its molar mass is approximately 28 grams per mole, so it's not big, and it's nonpolar with only LD IMFs. So it's going to want to expand. Azide is the active component in Na-N3 powdered airbags. So really, this is all part of E. So provide the Lewis structure and molecular geometry for azide. So let's do azide here. Azide is N3 minus, so that's going to be want is 8 times 3, 24, minus have is going to be 5 times 3, which is 15, plus 1 for that electron. So 24 minus 16 equals 8. Lock those into covalent bonds. That's going to be 4 bonds. So we have N, 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 boom, 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 2, 4, 6, 8, 2, 4, 6, 8, 4, 6, 8, minus 1. And this is going to be a linear molecule. Okay, so let's see below. And I believe that is it. So if we look at this, I know it's kind of dirty, but we started off with this first problem. This was a single replacement reaction where we did some stoichiometry with that, okay? And then we kept on going. And we did some photoelectron spectroscopy, and we did some Lewis structures around that, so you're going to need to know that. We then related that to, it's because of that. And we then related that to PV equals nRT. Went ahead and did another reaction. This was a synthesis reaction down here at the end. And we did our airbag